All right. Hi, MATH7502. You guys can hear me and see me, I assume. Yes. So, great. Okay. Just congratulations on your first quiz. And thanks for submitting all your quizzes and recordings. I know it's a bit of a hard thing to prepare it all, but thanks. Who has not done a quiz for more than 3 years, or a test or a quiz? Or is there somebody here that hasn't done like a quiz or a test for more than 3 years? Many years. Somebody's saying in the chat. Well, okay. It's always good to return to some things like that. Can I just get an indication on the how hard was a quiz? 10 being very hard, 1 being very easy, 5 being kind of what you expected. How hard was the quiz? 10 very hard, 1 very easy, 5 being what you expected. Okay. All right. So there's some variability. Okay. All right. Yeah, I couldn't ask too many things in this quiz. We didn't have too much content. Some of you might have found the notation a bit difficult, especially if you didn't do MATH7501. That kind of puts you in the realm of notation. Anyway, it's a quiz, and it is what it is. You'll see the solution with Sam and Walla in the practical. Are there any questions before we move on for about an hour of a lecture? No? Okay. So look, we stopped. I'm gonna share screen on maybe on I'll do it on this Chrome here. Let's see. Okay, so we stopped dealing with linear transformations in the last lecture, and I'll get back to that. But I'm not sure if even today, because it's time after a quiz, I want us to do something kind of a bit more enriching and fun than just move on directly with the kind of the mathematical material. So we're going to move here to number 2 in the list of exciting things that you're doing in this course, meaning things that have data science, machine learning, statistics applications. Okay, so we've already done clustering, and today we'll speak about the Perceptron algorithm. I don't think we'll really see what's called a convergence proof, but that may be something that some of you will choose to do as a project. Okay, so let me set the setting. So basically what we're going to do is we're going to speak about the Perceptron algorithm. And you'll actually find you'll find this in GitHub. You'll find this file, Perceptron. And we'll be going through this, this code that I created recently for the purpose of this lecture. Okay, you should probably see this in GitHub. You don't have to download it now or anything like that, but that's what we'll be speaking about. So that should be in here. Okay, and I've just pushed it. As you guys were doing the quiz, I was perfecting this. Or I don't know if the word is perfecting, but let's just say finalizing. All right, so let me start to give you some background on what this is. So we've already seen clustering, right? Now some of you know a thing or two about machine learning already. Was clustering supervised learning or unsupervised learning? So was clustering that we've seen, did that form in the, is that supervised learning or unsupervised? It's unsupervised, as this one said. So clustering is unsupervised learning in the sense that we only have our X's, okay? That's the case with clustering. We're in lecture 4, I believe, right? So I'll just write this here. Sorry, I should have done this right. And a lot of this course deals with supervised learning and through regression. And what we're going to do is least squares in regression for a long time. So the idea of supervised learning, whoops, that's a very big pen. The idea of supervised learning is that we've got X and Y. Okay, so, and we want to say something about Y. X is sometimes called our feature, our features, and Y is called our labels. Okay, and we want to say something about the labels based on the features. And the general idea is that we see the data, so we see X's, and then we see some Y's, and all of this together, this X and Y like this is a training data, and then we create a model, and that model can tell us something. Okay, that sounds, if you've never seen such a thing, that sounds perhaps very kind of loose what I've said, but we'll make it concrete in a second. Okay, so in supervised learning, so supervised learning. Problems fall into roughly 2 types. One type is called regression, and the other classification. Okay. So a lot of what we'll do in this course is regression, and specifically very simple regression, least squares, but actually very powerful. So you can go a long way with least squares regression. That's a lot of what we're going to do in this course. But today we're going to explore an algorithm that does classification. That algorithm is called the perceptron. And there's many algorithms for classification, many algorithms for regression, and the one we're doing today is the perceptron. So this is a classic old algorithm from the 1950s, and it's, in a sense, some people think it's kind of the birth of machine learning, even the birth of artificial intelligence, if there is such a thing. And we'll see how that works. It's a neat, simple algorithm that's based on a bit of linear algebra. Okay, so we're going to deal with a perceptron. So let's just make this slightly more concrete for a second. So say here, I'm going to put here on the plane, I'm going to put weight of individuals and height. Okay, so here, now, this is going to be, I don't want to be too politically incorrect, but it might be a bit of an ethnic thing, okay? So there's going to be some, here's a person like this with a certain weight and a certain height, right? That's their weight and their height. And here's another person, and here's another person, and here's another person. But maybe we have some people here, okay? Etc. Of course, this is all contrived. This is all made up data. Okay, so these people here, you'd say they're very perhaps tall, and maybe you'd use some words like maybe slim or something like that. And these people here, you'll say that they're short and perhaps stubby. Okay, or something of that sort. Okay, now assume that we also have these kind of we know where these people come from in the world. So you see, let's say these guys here, and this is an extreme case, okay? Just so you understand what I'm showing. So these guys here, they come from blue land, okay? And these guys here, they come from green land. I mean, maybe they come from Greenland Island, you know, Greenland. Does anybody, just a quiz, I mean, you've just done a quiz, so one more small quiz. What country owns Greenland? Does anybody know? Greenland, the island Greenland? Just to see that you're listening, or at least so you know. Denmark. Molly knows it's Denmark, right? Okay, so in Greenland we have Eskimos. They might actually be more in this category, actually. But anyway, so that's what we have. Okay, now you could think of going back here to the features and the labels. Our features, our X features are going to be the two coordinates, weight. Oh my God, cannot write. Weight, and height. Okay, so each feature of a person is their weight and their height. Okay, if this would be high dimensional data, then a person would have dozens or hundreds or tens of thousands of features, or maybe the features can even be pixels in an image. Okay, but that's a feature. The label of each person is just, you know, either the blue land or the green land. Okay, that's the labels. I think I've used a different green here. Green. Okay, so when the labels are falling from a finite set, in this case only two, but they can maybe have a few more labels, then this problem is called a classification problem. Now, our purpose is to look at the data, see this, and then create some rule that, and here are some models, some rule that maybe does such a thing in the, you know, this wouldn't be our model. And the model will say anything that falls to, say, below this line, if you see another person that you've never met, but you've already trained on the data, then you say, ah, yeah, that person is clearly from blue land. And anything that falls above this line, this squiggly line, this border, or whatever, that would be, say, a person from Greenland. Okay, so the name of the game of the model is to actually create this rule after you've seen some data points. I mean, that is the essence of this whole thing called machine learning. And that's a good part, not all, but it's a good part of what a data scientist does. Okay, so you create, you see the data, and then you have this model. Okay, and this is a classification model, but in this case, it separates the positive plane, this positive plane, you could call it something like maybe R+2, okay, because weight cannot be negative and height can't be negative. It creates it into the, it separates it into the blue region and the gray region. So that's what you'd expect a classification algorithm to do. And there are many classification algorithms, but we're going to look at this classic one called the perceptron. Okay, are there any questions so far? All right, so the general idea is that we've got these data points and we're gonna separate the data points, okay? Now, we're gonna make an assumption on the data points, and it's a bit of a strong assumption. And this assumption is that you can pass a straight line. Wait, I think I can do here somehow a straight line. No, I don't know, sorry, not sure. I'll just draw a straight line. Okay, you can pass a straight line between the data points. So the assumptions, I'll write it here maybe in red, assumption is linearly separable. Okay, so that means that you don't have, because for example, if you had a different data set, which was like this, and let me put here a few blue points. and then I'll put a few green points here in the middle. There's no way to pass a single straight line and separate these points, okay? So this one here is not linearly separable, okay? I mean, you might be able to do something like that, but that's not a line. Of course, there's methods for dealing with that. But we're here, and for many of you, this is the first time you're seeing a classification algorithm. And with the perceptron, we'll assume that the data is linearly separable. Now, the nice thing is that we don't have to have that the features are only two-dimensionals. We could also have the features three-dimensionals or five-dimensional or seven-dimensional. For example, if the features were three-dimensional, then, you know, I'm putting here, this is kind of, I'll call this F1, feature 1, F2, feature 2, F3, feature 3. And, you know, I'm going to put a few data points here. And you need to imagine these guys now floating in three-dimensional space. So we don't have just the weight and the height. Maybe we have the weight and the height and the age. Okay, age is maybe not for separating between countries or whatever. Okay, now in this case, you are not going to put a line between the 2 points. Okay, so a line's not going to separate the 2 points, but what we'll put is we'll put this plane. Now you need to imagine this plane here that I've put here. You need to imagine it kind of sitting between the green points and the blue points. Does anyone know what we'll call such a plane? Maybe you've seen this someplace else, etc. So this thing is going to be called a hyperplane. In general, a hyperplane is a plane in n-dimensional space that doesn't necessarily pass through the origin. This was a hyperplane in 2 dimensions. If you only had a single dimension, things are not as interesting. You know, the hyperplane is just a point. A hyperplane in 3 points is, okay. And the perceptron algorithm will find such a hyperplane, okay. And then after we finish training, after we finish looking at the data and finding the hyperplane and we have the algorithm, then every time we're going to get some new individual, we'll get their weight and their height, and we'll see where they sit in relation to the hyperplane. Okay, that's not going to be this wiggly plane, it's going to be a clean hyperplane. And that's how the algorithm works. Okay. So first of all, how do we specify the set of points in n-dimensional space? So now let's take Rn to be n-dimensional space, but for simplicity, we like to draw R2. Think of R2. Okay. So how can we specify a hyperplane? I mean, in R2, you know, you can tell me, well, this is just a line. Okay. But in Rn, in a line, you might tell me, oh, this is the intercept and this is a slope. This is one way of learning what the line is. Okay? But there's actually a different way that works for hyperplanes in any dimension, and we can visualize it like this in 3-dimensional space. But you know, otherwise we can't visualize it, but we use our intuition from 2-dimensional space and 3-dimensional space to visualize it. So the way we can visualize a hyperplane is we can think of some vector W, okay, in Rn, okay, and that vector is going to be perpendicular to the hyperplane. So let me, for simplicity, I'll go back to R2. Okay, I'll go back to R2, and I'll just draw a similar plane. It's going to be like this one. Okay, so draw like this one. Okay, so I want to now describe this hyperplane, and it goes on forever. Okay, so I want to describe the set of points in this hyperplane. So what I can do is I can take a vector that's normal to it, this W that's perpendicular. Let me make this W like that, and I'll say the hyperplanes are all of the points that satisfy W transposed X, the inner product of all of the points X that satisfy W transpose X, plus some constant B. Okay, and so the hyperplane is going to be where this equals 0. Okay, so the hyperplane let's write HP is the set of all points X such that W transpose X plus B equals 0. Okay, all the X here in R2 in this case. Okay, so this is how we can describe the hyperplane. This vector B describes the hyperplane. Okay, this vector that's perpendicular to the hyperplane. And for the purpose of the perceptron, this is actually going to be convenient. Okay, and it's also in general, so you can do this in n dimensions. In 3 dimensions, you'll take a vector that's perpendicular to the hyperplane. Okay. The magnitude of this vector doesn't really matter. So you could have normalized it. You could have taken the normalized unit vector. You could have taken anything else. But the point is, you're specifying all points X that are on the hyperplane are have an inner product with W that is 0. Okay, so that is a convenient way to specify the hyperplane. Now, once we have that, if you have such a specification for the hyperplane, then there's a question, okay, so you take a point, and I'm going to draw it like it's a black, and we don't know if it's sitting above or below. You take a point and you say, well, does that point sit above the hyperplane or below the hyperplane? Does it sit on one side or the other? So what you can do is you can ask, you can say, WTX, W transpose X plus B, is it greater than 0? Question mark. Or is it less than 0? And if it's greater than 0, it means that the point sits on one side. If it's less than 0, it means that the point sits on the other side. So Jonathan is asking, can you explain why W transpose X solves for hyperplane? So it doesn't solve for hyperplane, it just defines a set of points in the plane that look like this. Okay? So any point on this set, so take any vector on this set, okay? When you take the inner product of that vector with B, with W, you should get the constant B. Well, the constant negative B. Sorry, so this should be, well, this should satisfy it. I'm not sure I'm explaining it well. Let me see if I explain it, if I can explain it better later on. But in any case, this is a set of points that define the hyperplane. I know I don't have a great explanation. Sorry, at this point. Okay. So the question is, how do you choose W? Okay. Yeah, I'll try to come back with something better, Jonathan. So how do you choose W? Well, the thing is, this is now the perceptron algorithm is going to be one way of finding of describing such a hyperplane. And at this point in the continuation of the lecture, now what I want to show you is I just want to show you, hey, this is how this thing works. And some of you in your final project will dive deeper and just use some pretty basic mathematics to show why it works. Okay. But let's make it work. So let me go back to the this Jupyter notebook. Okay, so in this Jupyter notebook, you should be able to see. One sec, setting up just a bit more. Okay, so. First of all, you can go to this link. It's a good lecture in Cornell University that has more on the perceptron in a course specialized about machine learning. Okay, so okay. Oh, and okay. So this one is giving a description about the null space of W transpose perpendicular to the column space of W, but we still haven't gotten to that. Okay. And yeah, there's more comments. I'll move on for now. Okay, so what I'm going to do is I want to walk you through this code where we're actually, first of all, going to set up some mock data. As opposed to working with real data, we're going to set up some mock data. So I'll just explain this line by line so you see. So this M is kind of bounding box size of our world. Okay, so just to make things clean, we'll work in living between negative M and M times negative M and N. So we're going to live between -2 and 2 and -2 and 2 for each coordinate. So we're going to do this in 2 dimensions, okay? In this function data generator, it's going to generate, let me actually just restart the kernel here so we go from scratch. It's going to generate a default of 100 points, but we could specify a different number of points, okay? And it's going to generate them randomly. This is not the learning algorithm, this is just making up the data. So we're going to do set seed to make it the same on every run. Now here I am purposefully assuming that there is some W and B. So W is a vector pointing in the 45-degree direction. So that's the vector 1, 1. Okay, and B is 0.5. Okay, now I could have said anything else. I'm saying this is as though this is, so sometimes when we do machine learning and statistics, we assume that there's the higher power that has said the right thing, the right hyperplane. Well, this is like the right hyperplane. Okay, we won't know this. This is for the mock data. And what we're doing here is we're setting points which are, so it's an array of arrays where each point is a 2-dimensional X and Y. Okay, so it's an array of X and Y. Okay, and uniformly distributed between -M and N. We could have chosen anything else. This is just a way of choosing the distribution. Now, this is how we're going to now set what our data is. So this is, again, this is still not the learning algorithm. This is how this defining a function. This is a one-line function for the label Y, okay? And it gets a point X. It gets some point X. And what it says is it does the inner product of W and X. We don't need even this multiplication, Julia. Okay, it does the inner product of W and X. And adds B, and it checks if it's greater than 0. If it's greater than 0, that's if greater than 0, it'll make the point, we'll call it a positive point. So sometimes when we're doing classification and there are only 2 classes, it's convenient to make the classes +1 and -1. This will be a positive point. And if it's less than 0, we'll make it a negative point, just like that, okay? So on one side of the hyperplane, we're calling things positive. On the other side, we're calling things negative. And then our labels is just going to be this label function with dot. Dot is, again, dot is the broadcast operator applying label to each X point, okay? And then what we're going to do is we're going to return a tuple. I'm also kind of a bit more describing about this. And Julia, so return a tuple, which are the points and the labels, okay? You know, points, or let's call it features, and labels. This is the type of the data in supervised learning, features and labels. In unsupervised learning, when you did clustering, you just had the features. You just had the features. Okay, so we'll run this function. And then in the second cell, what we're going to do, it's going to take probably just a bit to run because of the first time to plot issue. So X comma Y, X is going to be the points from data generator, and Y is going to be the label. So you can get the return value from the function like this. And instead of using the default value of 100 points, we're getting 200 points. And then here, so this is a situation where we now know in our data, these are this point. But know that from this point on, we don't know W and B. Okay, so W and B were only here, up here, mock data, you know, mock values, or mock model. Or, you know, it's mock reality that we don't know. So at this point, we don't know W and B. And what we're going to do here is we're going to select all the point x that are with a -1 label, select all the point x that are with +1 label, so we'll call this x neg and x pos, and then we're going to plot them. Okay, you see here we plot the negative and we make them blue, and we plot the positive and we make them red. Okay, that's how we plot them. And if we were to put 10,000 points, that would have been fine. We have 10,000 points. Okay. Of course, these points are linearly separable by design. When you come to a real data problem, it typically won't be linearly separable. It won't be so nice because you'll have some, random points in here and there. But there are ways to deal with it. But at least for understanding the perceptron algorithm, just like that, we're dealing with linearly separable data. Okay. So in this data, you don't have any line that separates the points. And what we want is we want an algorithm that finds a W and a B. By the way, there isn't a unique W and a B. Linearly separable, you can slope things a bit, and W is certainly not unique because it can be much bigger and much smaller. Okay, there's a W and a B. And we want to find that. Okay, so I'll just show you immediately how this perceptron works. And this is this function implements the perceptron algorithm. Okay, this is the actual function that implements the perceptron algorithm. Okay. Is this going to work? Maybe, I hope it will. So let's just implement it like that with x and y. So the first thing we want to do is just find the number of points that we have. That's what we do in line number 5. We find the number of points that we have. And the next thing is we want to zero out W. Okay, so initialize W on as zeros. How many zeros am I putting here? How many, what should I have, 2 or 3? I'm currently setting 3 zeros, but that's what I put 3, right. Let me just go back here for a second and show you that we now do the following type of trick, which is a very common trick. It appears now, it'll appear often again and again, and it's the following. So we want to speak about the hyperplane W transposed X plus B. Okay, so and in the 2-dimensional case, W would be like the coordinates W1, W2. So W transposed is, let me just write, that's W transposed. And X would be the coordinates, say, X1, X2, okay, plus a scalar B, okay? And we're saying, is this greater than 0 or less than 0, okay? This equation is this one, all right? Now, what we often do, and we do this also with linear regression, we do it elsewhere, is we take this B term, and this B term, by the way, is sometimes called the bias, although the word bias is overly used in many ways. So this is these are, sometimes you call them the weights, okay? And if any of you have dabbled with neural networks are kind of the grandchildren of this perceptron, and they still have the bias and weights. So what we do is we can take the bias and the weights, and we're going to do a different thing. So what we'll do is we'll do something like W1 tilde, W2 tilde, W3 tilde times 1 X1 X2. Okay, and we'll ask if this is greater than 0 or less than 0. So what we've done is, instead of writing this as an affine formula meaning one where we had this additional bias term, we add another feature. We create another feature, and this new feature is going to be just a constant 1. It kind of stands for like the intercept, okay? This constant 1. So then writing the way I did it here, of course, we could have written this in different ways. This W2 tilde is just W2, and this W3 tilde is just W2, and this W1 is B. Okay. So it makes the problem a bit easier both to analyze and to implement. Okay. So we no longer have this, but we rather have this. Okay. And this is why we went from 2 to 3. Okay. Of course, we could have also just done, we could have done it differently, just so you see that I could have done. We could have just written W1, W2, W3, and put here an X1, X2, and a 1, and stuck this one as 3. And then, you know, we don't even need to use the tilde. Okay, just reorder things. Okay, so what I'm saying is here, we can instead of thinking about a separate, and there's quite a lot to this, instead of thinking about a separating hyperplane, it's like lifting the problem to one higher dimension and then just passing a plane directly through 0. So this hyperplane that's parameterized, that's perpendicular to W1, W2, W3, this hyperplane in 3 dimensions passes through the origin, okay? This hyperplane in 2 dimensions only passes through the origin if the bias is 0, but otherwise it doesn't. Okay, so this is how we've kind of that's a way to handle it. Okay, let me go back to the implementation. And you should be able to see that. Okay, so in this implementation, this 3 is initialized W0s. Note that it now also has the bias in there. Okay. And then forget about these 2 things. And let's now get to the essence of the algorithm. Okay. The essence of the algorithm is in, let's look at line 12 first. Okay, let's look at line 12. So this is going to be like many algorithms that learn things. It's going to be an algorithm that iterates over W, and W is going to change and change and change and change and change until we get the correct W. And fine, if we scroll down, what I have here is an animation, and you could run this too later on. Okay, so this animation shows you how this W is going to continue to change and change and change and change, and each time it's accommodating for a different point that doesn't fit, and W is being adjusted. And as a consequence, if the points are linearly separable, after a while, we get onto the correct W, or A correct. I say A correct because you can have several different things that separate. So you see, this is now after 157 iterations, it's stopped. And now this thing's just repeating, it's repeating in an infinite loop, this animation. The code for the animation is here. But before that, let's see. So what we're doing here in line 12 is make a prediction based on current W. So how does this prediction work? So the prediction simply does an inner product between W, and remember, this is our modified feature vector. This is a feature vector that has the new X, right? The X has shifted and have another one. And it's asking if this thing is greater than 0, then our prediction is positive 1, otherwise it's negative 1. I mean, that's how this classifier works. And now here we're saying if bad prediction. So on a specific point I, so we're looping over all the points I, and we're asking if we have a bad prediction. So if we have a bad prediction, then we simply make an update, and this is a key update step. So let me write here, this by the way should be just a Y, I believe. This is a key update step. So what do we do? And this is the magic of the Perceptron algorithm, and you'll by yourself, if you do this in your project, you'll see how the proof works. Okay, and you actually know enough mathematics now to understand this proof. So you have a good link to the proof here in in this set of lecture notes, but it's in many other places as well. Okay, but I like the way it's presented here. Okay, so what you'll do is you'll take the previous W and you'll add to it this thing. Now, let's just look at this thing. What is yi? What is a set of values that yi can take? I mean, yi cannot take too many values. What values can yi take? So y is our label. What values can our label take? The actual label. You guys are tired from the quiz, it's understandable. But 1 or -1, and somebody said 1 or 0, but we purposefully encode the labels not as 1 and 0, 1 as -1. And then this is just shorthand for if we got the wrong label and the correct label is 1, then let's add to W. Okay, add this point to W. And if it's -1, let's subtract this point from W. You see? Either add 1x, I'll write it short like this, or subtract it. Okay, so because we're either multiplying by 1 or -1. So these two lines are kind of the key. So line 12 and line 13. And now let's look at the bigger picture. So what does the algorithm do? So first of all, lines 9 through 22, this is end of while loop. So it runs supposedly forever, but not really forever, because if all perfect, if all points are classified, then stop. Okay, break. And now that breaks goes out of the while loop. So basically what this algorithm does is it tries to correct for each point, and if the number of misses is 0, it breaks. How does that work? At the start of each while loop, we set the number of misses to be 0. And here we iterate try all points. Okay, so we iterate over all index points, over all I points. We make a prediction for every point according to our current model. And then we see, if we have a bad prediction, then let's adjust W. And of course, we now had a miss. So then we did a misses +1. Okay, now if we went on all the points and there were no misses, then we finally get here, misses are 0, and we finish the loop. So there might be a few iterations of this outer loop, right? Now, if the points are, what's going to happen if the points are not linearly separable? What's this algorithm going to do if the points are not linearly separable? If you actually cannot find a hyperplane that can separate the points, what's this algorithm going to do? It's going to run forever. Very, very bad. Very bad. Stuck forever. Okay. So of course we need conditions for that, right? But our assumption here, this is so you're seeing the theoretical, it will never end, right? Run forever. You're seeing the version here that assumes the points are linearly separable, and then breaks here after all points have been set. Still, it's not obvious that this thing should work, but there's actually a proof that it will work. Now, line 16 is keep history for the animation, not part of algorithm. Okay, so often when you run an algorithm, when you run it kind of in production, when you're using it, you don't need to kind of record all the steps. But here, I wanted to make this little silly animation, so I'm keeping the history as the algorithm is running. So each time in the history, I'm kind of recording this tuple, which is the weights W and the point that was used. So the question is, the data has to be perfect? Yes, in this version of the algorithm, the data has to be perfect. Okay. However, I must tell you something about this data perfect thing. It's not just that the data has to be perfect, because what you can do is you can actually add more dimensions sometimes, and then you will find a separating hyperplane through the data. So there's more to that. You'll see more about this in the machine learning course. Okay, so sometimes the data is not separable in 2 dimensions, but when you move to 3 dimensions, it is separable. And if that's not good, you move to 4 dimensions and it is separable. So sometimes you'll you'll kind of inflate the dimensions of the data, just like we did with the intercept. We won't speak about this more. But also to make this robust, you want to kind of throw away some outliers. So this is the theoretical version of that. Still, it's a central thing. Okay, so let's run this algorithm. So let's hope I didn't break this code with this minor kind of changes I did. And this is learn perceptron. Okay, so learn is like train. So we have our data, just so we see, we have our X, our 200 points, and we have our Y, our 200 labels. Yeah, the positive one, a negative one, etc. Okay. And what we're going to do is we're going to learn the perceptron on X and Y. And now it says Y not defined, because someplace here inside this perceptron I had Y instead of Y, and Y here. Okay, that worked. And extended W is going to be this W. I call it extended W because it's also a W for the slope, and it also returns a history. Okay, so the intercept is extended W at 1, the first coordinate, and the actual W, the vector that is perpendicular to the hyperplane, is the extended W on lines 2 to end, or in this case, it's just two-dimensional, okay? Just two-dimensional. And then we can show what B is, so we learned that it was a 5 and W was a 10 and a 9.7. Okay, that's 10, 9.7. Now, look, the W that we got here is not the W that we use to create the data. To create the data, we use this W11. But all you need for describing a hyperplane in a W is the general direction. Okay, so we could have at this point, we could have also done, if we just wanted, we could have done extended W2 to end, and then we do also W equals W divided by normal W. We probably need to do using linear algebra for that. Let me put it at the top. Use the norm, okay? So W equals W divided by norm W. And you see now this W is like a normed vector, right? So it has about, yeah, it's like the vector, it's pointing in roughly the same direction as the vector 1, 1, but it has, its norm is root 2, is 1 on root 2. Yeah, 1 divided by root 2 is this 0.7 roughly. Okay. Now just to see, let's change our mock data. So let's make our W here 2, 1. Okay. So I'm going to change the mock data and make W 2, 1. Okay. So now the hyperplane slopes in a different direction. If you want to see more of it, you know, let's put some 2,000 points. Okay. And let's run the algorithm again. And you see now you've got a W that's pointing in a different direction. Okay. Let me return it to what it was, simply because it'll match the animation. Just 200 points. Okay. So now let us just plot this. Okay. So for plotting this, what we're going to do is we're just going to plot the negative points, we're going to plot the positive points, and then we want to plot this hyperplane. Now, for plotting this hyperplane, we want to plot it between, remember our points live, their x-coordinates live between negative m and m. Okay, so the calculation that we do here, let me write this, I'll just write it here. So what we're doing is we're doing like W1, oops, sorry. We're doing W1, write it like that, times W2 with inner product with m, let's say minus m, and the, let's call this x2 plus b needs to be 0. Okay. You'll see what I'm doing here. So I've written here the inner products of these things. Let me just, to be more precise, I'll put a transpose here so things are column vectors, okay? So this is just an inner product between the W1, W2, and now we want to see where it is at the point minus m. So this minus 2 is minus m, okay? And x2 is like your horizontal coordinate. I just don't want to use the word y because y is used for the label. Okay, so then if you solve this thing for x2, okay, so solve the above for x2 and you get x2 low. Okay. So that's just to find this coordinate here for actually making a plot. Sometimes you need to work a bit, you need to do some algebra when you're making a plot. And this is similarly, instead of negative m, instead of x1 being negative m, x1 is positive m. Okay, so that's it. So, you know, similarly, for x1 equals m instead of negative m. Okay, so then you can plot on the point negative m, x2 low, x2 high, line with 5, this black line, that's actually our hyperplane. And that's it. That's it. This is an implementation of the algorithm. And here, I'll just explain this quickly. So I'll run this as I explain it. So here, just so you see how you can make an animation. So because of, and this is something you might want to do for other things later on. So you, maybe we don't even need this pie plot. We've set it above here. Anim is an animation object, and then we're going to run over all of the history. Okay, so this is, let me just comment this, we'll iterate over all of history, but also keep the last point of history for 20 iterations. The reason I want to keep it for 20 iterations, if you show how an algorithm works, you're going to create, we're doing frame by frame animation. Yeah, this is like Walt Disney in the 1920s, frame by frame. So the way you do frame by frame animation, you draw and you call frame. Okay, this records the next animation frame. And then you can make these animations and you can put them on your Twitter account or something. Okay, so we're doing this frame by frame animation. It's recording these frames. I think this is also in GitHub. It's been uploaded to GitHub, the animation itself. And after all these iterations, at iteration 157, when this thing is actually fitting for all the points, you want it to freeze for a bit. So that's why you keep kind of the last 20 iterations. Okay, so it's scattering the points, it's doing all these things, and this annotate creates a text. You see it's holding the things a bit. Oh, it's holding the animation a bit, and it will probably restart in a second. And that's it. That's what I wanted to show you with this code example. And again, this will be relevant. So if we look at your project, so let's look here at the final project. So your project should have a demonstration for 3 out of the 6 topics appearing in data science use case. This was one of them, topic 2, perceptron. We already did topic 1, clustering. Okay, so we're kind of little by little moving through these topics. Okay. Now, I didn't explain the crux of why this thing works. So the heart of why this thing works is actually this step that takes W and updates it. So it updates it to adjust for a new point. Okay, it adjusts for a new point, but it does it in a greedy manner. And also, if you go to the lecture notes here, you'll see the proof. So if any of you choose to do this in the final project and you want to kind of go through the steps of this proof, and the proof is if the data is linearly separable, then this algorithm actually finds a hyperplane. And there's even a bound on the number of steps that it works in. Are there any questions? No. I feel a bit tired and I didn't even do a quiz. Oh, okay. So there's a question why we don't need a learning rate. So in this specific algorithm, you kind of work with a constant learning rate. You could have also had a different version that iterates slower or faster by multiplying this by a constant, which is sometimes called the learning rate. But this one just works iteratively without the learning rate. Okay. And look it up. Look up the Perceptron. It's really the classic machine learning algorithm. Any more questions or thoughts? Okay. So in the next few minutes, let's now move just to a bit more core content, and we'll see where we're going as well. Okay, so I must say that your assignment 1 and quiz 1, from my planning perspective, I wanted to have some deeper things in both assignment 1 and quiz 1, but we didn't move so far in terms of kind of the core linear algebra, right? So now we're going for about 2.5 weeks or so. We're gonna do quite a lot of things until we get to least squares data fitting. Okay, well, on least squares in general. Okay, so let's go here to core linear algebra with Julia and just I'll overview what are these things. Okay, so you've done this and you've done this. Okay, so you've done 1 and 2. Okay, and we were at the entry point for 3, which is linear transformations in vector spaces. Okay, so I'll speak now for a few minutes about linear transformations, and then next week we'll have a full 3 hours where we could speak about independence, span, vector spaces, the column space, the null space, the 2 other spaces, the relationship between these subspaces. We'll also see how to do change of variables when we do multivariable integration. And we'll move on to orthogonality, okay? And then this is kind of, in a sense, number 4 is the heart of the course. So we have quite a lot to do when we speak about these things next week. Now, in terms of linear transformations, I don't think I know. So what we stopped last week here, and I think I wrote on the notebook, that is, I do think, with linear transformations, and we saw a key result at about the same time, exactly 168 hours ago. 168 hours is a week. So what was this key result about a linear transformation? So a linear transformation is a function from Rn to Rm that satisfies this property such that when you stick in a linear combination of vectors, so x, y are vectors in Rn, and f of x and fy are vectors in Rm, and alpha 1 and alpha 2 are scalars. So when you stick this inside the linear transformation, what you get is a linear combination of the outputs. And what was this key result? I think what I should do, I should just maybe go and do it again, and then I'll also suggest a few videos to watch, okay? Also dealing with these linear transformations. Okay, so I'll go back here to the writing pad. Okay, so linear transformations. So this is kind of finished with this. Linear transformations. Once again, okay? So our linear transformation takes linear combination of two vectors and returns a linear combination of the outputs. This is not true for many transformations. So for example, if you try to do this, if you try this with the F from your quiz, that won't work, F from quiz. Okay, it just won't work. So you can't stick in a linear combination of two things in the quiz and get the linear combination of the outputs. Okay, but for linear transformations, it does. Now, if the transformation is of the form a matrix A times X, then this thing clearly works, because then you'd say f of alpha 1 x plus alpha 2 x y is A alpha 1 x plus A alpha 2 y, and that's alpha 1 ax plus alpha 2 ay, and these guys are just f of x and f of y. Okay, so that's obvious. That's obvious that this is a linear transformation. But what we ended with last week is perhaps not immediately obvious at first, but that is that every linear transformation has a matrix A. So every linear transformation has a matrix A. Okay. And the way to see this is to take some input vector x and to represent it as x1 times e1 plus x2 times e2 up to xn times en. So let's just mark these e1, e2 up to en. Okay, the unit vectors. Okay, so it's like taking the vector and making an accordion out of it. And now, I'm sorry, I'm repeating this, but it's just so important. So it's important we see this. So now you could say that f of x is f of, and now I'll just write this in a neater form. Okay, so I'll write sum of I 1 to and let's say that the transformation is from Rm to m. So I say 1 to m of xi ei. Okay, that's what it is. So we've got, am I correct? We've got n coordinates, yes. Okay, m coordinates. And then we can say that that is the sum of I 1 to m. This is slightly different than the way I wrote last week, then xi times f of ei. Okay, because you treat now these xi's, they're like the scalars, they're like the alphas that you've had before. Okay, and ei's are these vectors. So this is because of linearity. This is because it's a linear transformation. And this you can write as, you can now take a matrix which has f of e1 as a first column and f of e2 as a second column and f of en as the last column, and multiply it by x1, x1 through xn. So that is A times x. Okay, so every linear transformation has its matrix. Every linear transformation has its matrix. Now, just to see that this kind of holds, and we have 2 minutes, I'll do this in 2 minutes. I also did in MATH7501, but without speaking about linear transformation. So this, I think, was in the second week of MATH7501. So let's think about the rotation transformation. So let's think about the transformation that takes us from here, that takes a vector here and rotates it by angle theta. Okay, and rotates it here. Okay. Now, if you take for a second as an assumption that this transformation is linear, let's see how we can find the matrix of a linear transformation. Okay, so this gives you a recipe for actually finding the matrix of a linear transformation, and it's a great recipe. It just means apply your transformation to E1, you get your first column. Apply transformation to E2, you get your second column, and so forth. In this case, a transformation F takes a vector in R2 and gives a vector in R2 where it is rotated by theta, by angle theta. Okay, so what we need to do if we want to define f of x as some matrix A times x, okay, let's call it x1, x2, this 2 coordinate of x. Okay, so let me write here x1 of x2. All we need to do is we need to write here, for this, we need f of E1. We need to ask, what happens to E1? Now, I'm going to ask you to watch some 3 blue 1 brown videos, and they just call in 2 dimensions, E1 is sometimes called I bar and E2 is called J bar. And in 3 dimensions, you've got the third one would be K bar or something like that. Okay, the point is what happens to E1, and this one is what happens to E2. So I'm effectively out of time, but I'll ask you actually to think about it and get the rotation matrix. Get the rotation matrix. So if you stick here in E1, so what you're going to do is you're going to stick here. E1 is the vector 1, 0, and you rotate it by angle theta. And ask yourself, where did you land after you rotated? If you moved from 1, 0, so you actually moved on the unit circle by an angle theta. Where did you land? And for those of you that didn't do enough trigonometry or haven't done trigonometry recently, you'll review what cosines and sine means. So that's also important, okay? And you'll take the vector E2, this is a vector E2, and you'll rotate it by angle theta, and you'll ask where you will land. And then you'll get the rotation matrix. So I'll suggest this in an email as kind of self-study. And I think that that Sam and Walla might have a bit of time in the tutorials as they follow they show the quiz solution afterwards. So you might develop this with them as well. So this is like an example of how you say, oh, I have a linear transformation, it's rotation, okay? You can argue why it's linear. You can argue why rotation satisfies this property. Well, because if you rotate in one direction, rotate in another, you can kind of break it into the sum of rotations and things like that. You say, what is the matrix of that linear transformation? Okay, there'll be a matrix for every angle theta. And you just develop it by applying f on these unit vectors. I think I should stop. Sorry, I'm a bit over time. Are there any questions? No? You're probably tired. I'm a bit too. I stood today 3 hours in line to get COVID tested with my daughter. We're probably okay, but I'm now in quarantine. I'm sure we're okay. Statistically, we should be okay. But COVID testing is kind of, you do it for the masses. So she was in a hotspot and has minor symptoms, but the queue was 3 hours long. C'est la vie. So, yeah, it's okay. So there was just a question how to calculate theta. Theta is a given for the rotation matrix. So you'll do this either in the prac or with me next week, and I'll also send an email about watching some 3 blue 1 brown videos. Any final thoughts? Okay, so let me wish you all a good evening, night here in Brisbane, or a good late afternoon in Asia. And see you next week. Bye.